Welcome to Brain Vision.
We're going to look at problems 102 and 103 together because they analyze the same structure. So we have this cable here that has a uniformly distributed load that is a function of, it's not a weight. Again, if it were a weight, we'd have a little different analysis. So it's just a load. I didn't really draw the support structure on here, but it's basically a load that is uniform in the x direction. So the function here is a function of x, and that's a constant, not a function of s, which would be the length along the cable. So at any position along here, you will get the same value. And again, that makes a difference as they show in the chapter, that if this were actually a weight, then this would be a function of s, where you are in this, not where you are horizontally. So we can, given the boundary conditions, if we set this to set our origin. Actually, I'm not sure why I wrote that there. That should not be. So if we put our origin here at the low point of our cable, we'll get that our two constants of integration are both 0. And so y is given by this value, or this function. So we have a parabolic curve. And then we know that at L/2, which is, L is 50 feet in this case, so this distance here, y must be 6 feet, because it goes up 6 feet. So from that constraint, we can find out what the horizontal load is, and then this one will be equal and opposite. So that is L squared W naught over 48. Plugging that into here, we get that y equals 24x squared over L squared. Now they ask us for in their first problem, for the let's see here, to determine the maximum tension, or determine, let's see, the load that is capable of holding before it gets a maximum tension of 3,000 pounds before it breaks. So we know that the maximum tension will occur at where the angle here, or cosine of the angle between the tangent to the cable and the horizontal, is a minimum, and that will occur because of symmetry in this case at both of these points. So we can figure out what that angle is, because we can look at the derivative of this curve at this point, and then that is the tangent of the angle at that point. So we can take the derivative, plug in L/2, and we'll take the inverse tangent of that, and then take the cosine of the angle, and basically with some trig identities and manipulation, we get that the maximum tension is 1/48 times the square root of 1 plus 576 over L squared, all times L squared times omega naught. And that needs to be no greater than, at least, 3,000 pounds. If L is 50, then we can solve for W naught, and that turns out to be 51.9 pounds per foot. Now in problem 103, they actually give us W naught, or W here, and we want to find the maximum and the minimum tensions. So we can go do the same analysis. The maximum will again occur at these 2 points. The minimum will occur when this is as large as possible, and in this case that would mean that this is 1. So we can go through the same analysis, but now we know what W naught is. So we can plug that into here, and we get that the tension, or plug that into here, we'll actually have the same equation here as before for the maximum. We can plug that into here, and then figure out that the maximum is 14.4 thousand pounds, or 14.4 kip. And the minimum will be when this is 1, so that's when we have FAX, and we know FAX from here, and that turns out to be 13.0 kip.